Hey, welcome. So, before we can even dream of talking about big physics concepts like motion or force or energy, we have to get a handle on one single super powerful idea: measurement. And here's the thing, without measurement, physics, well, it just wouldn't exist. So, let's dive into this foundational topic of units and measurement.
Just think about it for a second. How in the world do we actually know the distance to the moon? Or how do we calculate the speed of a car? Or even figure out how long it takes for a planet to go around the sun? You see, from our day-to-day lives to the wildest scales of space exploration, absolutely everything comes down to our ability to measure things accurately.
All right, so let's get into our first big idea here. Why does measurement matter so much? It's because measurement is what gives meaning to all our numbers. It's the one process that makes science reliable, repeatable, and something we can all agree on.
And you know, what's so cool about this is how simple the definition really is. At its very core, measurement is just about comparing something you don't know with a standard you do know. So if we say a table is 2 meters long, 2 is the number, and meter is the unit, you absolutely need both for that to mean anything. The number and the unit, they are team, totally inseparable.
Okay, so with that in mind, let's see how this idea builds the actual language of physics. The words of this language are what we call physical quantities. They're how we describe the entire universe in a way that's super precise.
And these quantities, they basically come in two flavors. Over on the left, you've got your fundamental quantities. Think of these as the absolute basic building blocks, like length, mass, and time. They stand on their own. Then on the right, you have derived quantities, like velocity or force. And we literally create these by combining the fundamental ones. Velocity, for example, is just length divided by time. Simple as that. Now, you can probably imagine that if everyone had their own set of fundamental units, things would get chaotic really, really fast. And historically, that's exactly what happened. Different places used different systems like CGS or FPS, and it created a ton of confusion for scientists trying to share their work. So what was the fix? Well, it was pretty obvious. Scientists needed a single common system so they could actually talk to each other without constantly converting everything. And that solution is the International System of Units, or as we all know it, SI. The entire SI system, believe it or not, is built on just these 7 base units. You've got the meter for length, the kilogram for mass, the second for time, and then 4 others for things like electric current and temperature. Each one was picked because it describes a fundamental piece of our universe that can't be broken down any further. Literally every other unit in physics is just some combination of these 7. They really are the bedrock. Okay, so we've got our universal language. Now let's look at a few tools that physicists use all the time to handle the numbers they get from their measurements, focusing on being precise and clear. First up, significant figures. Look, no measurement is ever 100% perfect. Significant figures are our way of saying how precise a measurement really is. They include all the numbers we're totally sure about, plus one last one that's a bit of an estimate. So if you see a measurement of 1.62, you know it has 3 significant figures. And that tells you something important about the precision of the tool that was used to measure it. But what happens when you're dealing with numbers that are just huge? In physics, you run into unbelievably large or incredibly tiny numbers all the time. I mean, trying to write out a number like 150 billion with all those zeros is just clunky, and it makes doing math a real pain. And this is where scientific notation comes swooping in to save the day. That same 150 billion gets written cleanly as 1.5 times 10 to the power of 11. It's not just about saving space, it makes the calculations way faster, much clearer, and you're way less likely to make a mistake. It's an absolutely essential tool. All right, our final tool is kind of like a physicist's secret weapon. It's called dimensional analysis. And it's this amazing way to check if your equation even makes logical sense before you start plugging in any numbers. So here's how it works. Every single physical quantity can be broken down into its fundamental dimensions. Mass, which we note with a capital M, length with a capital L, and time with a capital T. So as you can see, velocity is just length over time, or LT to the minus 1. And force? Well, force is mass times acceleration. We know mass is m, acceleration is length divided by time squared, so that's LT to the minus 2. You put them together, and the dimension for force is MLT to the minus 2. And the rule here is so simple, but it's incredibly powerful. For any equation in physics to be right, the dimensions on the left side have to be exactly the same as the dimensions on the right. It's just like balancing a scale. If the dimensions don't match up, your equation is wrong. Period. End of story.
Let's try it out with this real-world example. The period of a pendulum, which is t, obviously has the dimension of time. Easy enough. Now for the right side. The length L has the dimension L, and gravity g is an acceleration, right? Which is length per time squared, so its dimensions are L over t squared. Okay, so inside that square root we have L divided by L over t squared. See that? The L's cancel right out, leaving us with the square root of t squared. And the square root of t squared is simply t. The dimensions match perfectly. It works!
So let's wrap this all up. What's the big takeaway here? Units and measurement aren't just some boring topic we have to get through. They are the absolute backbone of all of physics. They're the tools that let us measure, compare, and finally understand the universe around us with amazing accuracy. If you can master these basics, the rest of physics just starts to fall into place.
In the end, it really all comes down to this. When you stop and think about it, measurement is so much more than just a bunch of numbers. It is the language of science itself.